So next talk is Wisening Assertions, Live Bayesian Reasoning for Probabilistic Correctness by Joshua.
Hello. Is all the audio good? All right. So today I'll be talking to you about some new work I call Wisening Assertions. My name's Josh, and I'm a first-year PhD student at Cornell University. So this work is about assertions. And the first argument I'm going to make to you guys is that assertions are a really good way of programming. Because in this community, we care a lot about correctness, but we should take advantage of the fact that as programmers code, they think about correctness. And a lot of times they write down their thoughts about correctness. Sometimes they just do it in the form of comments. You write down some arithmetic, you put down a little comment that says what properties you think should hold about it. You do some data structure manipulations, you write down some properties about the data structures. This is a really good pattern, but it gets even better when you formalize these comments as assertions. Assertions are statements in the native language where the code cannot continue executing unless the condition is true. Just like we saw in the earlier talk, this form of dynamic validation and verification is very, very strong, but has a serious drawback. It's expensive. Sometimes it's really expensive, especially in these particular cases of assertions that I want to enable. We're going to look at this little code snippet here to sort of motivate the type of assertions that this work will allow you to write. This is an update to a data structure. You're inserting a key and a value, and you do the update. We're not concerned with that part. What we're concerned about is that the programmer goes in and they assert two things afterwards. They assert the update actually succeeded, and then they assert some complex invariant about the data structure. Maybe that the binary tree is still balanced, something like that. And now this is a really good idea. If this is the way you write your updates to a data structure, there is no way for your data structure to ever lose these key invariants, and whole classes of bugs are preemptively eliminated. But the problem here is that this could be a really efficient update, maybe an insertion into a hash table, but this is never efficient. This is always going to be linear in the size of the thing. So in this code, you spend more time checking your assertions than you do actually executing code. And this is clearly not a feasible situation. In real life, people react to this in a couple simple ways. The first is they just go ahead and comment out these assertions. In fact, in the real backend code this is based on, that assertion about the complex invariant was commented out. I had to remove the comment to show it to you guys. The other thing that happens sometimes, you run these assertions when you're developing locally on your laptop, but then when you deploy to production, you disable them all with a compiler flag or something. And when you do this, you sacrifice huge amounts of potential robustness. Test data can just never be as comprehensive as production data. So what this work is going to do is it's going to automate the process of turning assertions off to make them feasibly runnable at scale to a degree they weren't before. So before I give you the formality of it, let's think about what it would look like if you wanted to automate the process of turning assertions off. Let's say you have correct code. If your code's correct, you're going to make the assumption that your assertions are going to pass. This should be a property of the way that you write your assertions, and also just what I mean by correctness. But here's the slightly interesting part. Let's say that there's a bug somewhere in your code. It's not certain that your assertions will fail, but I'm going to say it's likely. I'm going to lower bound the probability. Maybe it's at least 1/10. Well, this is all just motivational. Let's do some back-of-the-napkin math, and let's say that you observe your assertion passing 43 times. Well, write it out. You have at least a 99% chance that all of your code is correct. In fact, if you want to visualize this a little bit more, as your code executes and you see the assertion pass more and more times, you can just assume that the probability, you can conclude that it's very, very likely to be correct. You should be able to do something with this information that allows you to turn the assertion off. In particular, let's do it this way. Let's say that you choose a desired level of confidence for your assertions, like 99.9%, 1 minus epsilon for your favorite epsilon. And let's say you choose this little magic expression. You execute your assertion not all the time, but with the frequency equal to that desired probability minus the prior over 1 minus the prior. Well, that thing will decrease. That frequency will go down over time as the probability goes up, and you'll get behavior that looks a lot like this. That's the same curve from before for the probability of correctness. The dashed line is this little formula right here, showing you that the frequency with which you execute your assertions will start to go down. This is the process that I call wisening for your assertions. Now, wisening assertions have a huge benefit, which is that your assertions have eventually zero overhead. This is a similar curve, but it's showing you that the cumulative cost of executing your assertion stabilizes pretty quickly, in contrast to regular assertions where it keeps climbing forever. This enables you to fearlessly write your expensive assertions thinking of that motivational data invariant one we saw before. Now, this is the motivating idea of this work, and we could stop here. But that would be a software engineering talk, not a PL talk. The interesting PL part comes when we start trying to think about the differences between different assertions. So let's just say I have mystery code, some code on the left with an assertion, some code on the right. The assertion on the left targets one variable, but the only important part here is that this variable depends on the entire code snippet for its computation. And on the right, we have a different assertion, but that assertion depends only on that latter half of the code snippet to compute its value. We can ask the question, we should wisen these both, but should we wisen them at the same rate? Well, the intuitive answer that I'm going to posit to you is no, we shouldn't. Assertions that depend on more code, you learn less about each given line when it passes, so they should wisen more slowly, as is kind of reflected right here. But that's just intuition. To formalize this idea, I want to give you something called blame. Blame is going to be a probabilistic event, in the normal probabilistic sense of the word event, talking about information flow. The event that on a given execution, there's an explicit flow, an implicit flow, whatever type of flow you like, from an expression to the point that an assertion is made. And this is just a formal definition. But the interesting part of it, we get, maybe if we zoom in a little bit, we can look at that same room variable we were asserting about before, and we can look at the code above it. And we can see that there are some lines, like straight line code, not inside any conditional, that always contributes to the computation of this room. And this is shaded with very high blame, because we always learn something about that by observing this value. Other code that's deep inside some conditionals is a little bit less shaded. We're less likely to have learned something about this code on given execution. What we're seeing here is that blame is not a binary thing, but it's a continuous probabilistic notion. Some lines are just more blamed than others. To figure this out, we use information flow type checking. And I'm going to run through a quick little example of what this looks like here. But if you're familiar with the notion of path conditions, it's going to look a lot like that. Let's say this is our line right up there, and that's our assertion. We want to figure out the event of blame between them. Well, this is a hard thing to reason about directly, so instead we think of another class of events. I'll call them pies. These events that a branch is taken or not. So I'm going to try and write down this blame event in terms of these pies. I'm going to note this, that there are basically two ways that this serve Q variable can end up depending on this request to variable. The first one happens inside both of these two conditions. So I'm going to annotate that with a conjunction of those two variables. And the second way, it's another case, happens just inside this little pi3. So that gets annotated with just that, but it becomes disjuncted into this formula. So this is telling you that this blame occurs if I take both of these branches or just that one. And this is true. This is a probabilistic equation. And now I can use this to write down this omega, which is the probability that this blame occurs, in terms of the probabilities these branches occur. But probabilities that branches are taken a certain way is something we know how to reason about in PL. This is branch prediction, and there are lots of fancy things you can do here. So you can run your branch predictor, get values, and now you have values for these omegas. And so the question just becomes, what can you do with them? How can you solidify, land the intuition that we saw at the beginning of this talk? Well, let's say this is you have your program for each line, write down a prior probability for each line that it's correct. So let's do that. We have a bunch of lines, we have our prior probabilities, and then something happens. An assertion passes. We can do something with that information. We can perform a Bayesian update. We can now compute the probability that lines are correct given this information. And now I'm eliding some details here because I do a lot more work to model this, but basically you get an expression that looks something like that. You can write down the new probability in terms of the old one and the blame of that line. In a simple case, let's say you figure out a blame of 1/2, you get a little wisening factor that looks like that, which is like a multiplicating averaging that brings it a little closer to 1 every time it executes. For different blames, you're going to get different speeds of wisening. But what they all have in common is that they have eventually zero overhead. They take a constant amount of cost, whereas traditional assertions, the cost keeps on climbing forever. And I claim that this enables you to go ahead and write those expensive assertions fearlessly, enabling new programming. There are some other nice advantages of this work. All I talked about so far was what happens when assertions pass. But they don't always pass. Sometimes they fail. And when assertions fail, you want to do fault localization. You want to figure out maybe where your bug is going to be. And these prior probabilities POPL that I was writing down are a great starting point for where those bugs could be. And this is a whole field software engineering people care about. Also, code is known to change. When code changes, you write down the set of lines that changed. You just reset their prior probabilities to the cold value. And all of a sudden, the right reassertions get re-enabled exactly as much as they need to be re-enabled. And that's it. And finally, and to some of you, this may be the most exciting application. If you're not the type of programmer I told you about earlier who's just chomping at the bit to use assertions, but you're the type of programmer who doesn't even know where to begin placing them, I can help tell you. I can use this. These are all differentiable functions to help you nicely optimize the placement of a given number of assertions that maximizes this sort of probabilistic coverage over the rest of your code base. Thanks for listening. I hope you found this compelling.
Any questions?
Hi. I'm just curious about a comparison between this and property-based testing. When should I use assertions with what Wisening? And when should I turn that into a property-based test and only run it on generated input?
Can you give me a 10-second summary of property-based testing?
Instead of writing a unit test where I just test on some data, I write a property I want to hold and then generate a whole bunch of test cases randomly.
So first of all, those generators are a handicap. Like, there are limited cases which they can write, and so this will work for absolutely any code. Like, the idea here is, like, a lot of PL starts from the bottom up. We start by working really well for simple cases, such as when we can generate large examples of tests from a condition, or when we can perform static verification. We start, like, expanding the scope of what we can statically verify. This is meant to go from the top down. This is meant to start with any arbitrary code you want to write, any conditions you want to write, like very, very complex assertions and placed anywhere, and then allow them to be, like, verified a little bit better. So I'd say that if you're not in this room, you should be using Wisening assertions. If you're just a software engineer, you should be using Wisening assertions. And maybe someday property-based testing won't meet in the middle with it. If that's compelling. I know it's a little high level.
Hey. So it seems like your blame calculus takes care of, like, different rates of wisening depending on where the assertion is in the code, but also how likely, I mean, assertions usually fail for some very specific inputs, right? So, like, some corner cases. So I might have seen this assertion pass a million times because those were, like, my normal inputs. And then there's, like, one freak input comes in where it will fail, right? So how does your technique take this into account at all? Does it look at the inputs?
So there are a couple answers. One hypothesis is that bugs like that are common, and a lot of times they have to do with control flow. There's, like, a case that will only be hit on some rare input. And the blame calculus is meant to identify exactly those cases. It's meant to find those branches that are taken one way 99.9% of the time. And if those exist, it's even a little bit evident in the math here. Then if that 1 minus omega gets really big, this thing wisens really, really slowly. So I can't eliminate the possibility of those bugs, but I do penalize that really heavily to make those assertions wisen slowly. That's one answer. The second quick answer is this sort of resembles training on an input distribution. So if you have an input distribution and there's something that's just not included in that, I really can't handle it. But I do have methods of thinking about maybe how I could observe changes in the input distribution.
I'm sorry, probably I should stop here. So the next speaker, would you please come to front and prepare for the devices? And let's have very, very short question.
Well, just very quickly, what happens when the distribution of input changes?
Well, my hypothesis is that it'll be reflected in what your branch predictor sees, basically. Those events, pi will change, and then I'll be able to live update the rate at which these assertions wisen to handle the fact that now coverage that used to be very good is now very poor.